all this together to specifically look at the well-fed state and the fasting state. So hopefully we'll get there. So we've already talked a little bit about the role of the phosphofructokinase 1, but now we're going to look at also the phosphofructokinase number 2, a similar enzyme in regards to the work that it does, as well as also the regulation of the phosphobisphosphotase enzyme. So this additional level of regulation. And again, I want to emphasize the regulation in regards to glycogen synthesis and breakdown, and how this plays a role in giving us that energy that we need very quickly to run away from that tiger in the response to a fight or fright mechanism induced by the epinephrine receptor and release of those particular activities in the IP3 receptor system to activate the phosphokinase B. But again, we're going to have a little look and differentiate between what occurs in the muscle versus the liver when we look at glycogen synthesis and breakdown. And also, again, we're going to keep an eye on this phosphorylation and dephosphorylation. And this is going to have an impact on glycogen importantly. And I want you to really emphasize and think about, we still have problems understanding the issue of phosphorylation and dephosphorylation and what it does. Originally, people thought when they first realized phosphorylation is working, is that phosphorylation controls everything. If we phosphorylate something, it stops it. If we dephosphorylate it, it basically makes it activated. But then we started seeing the vice versa. So there's actually some very interesting contradictory measures in regards to the process of the impact of phosphorylation, whether it has a positive allosteric modulation or a negative allosteric modulation. So we're still not there fully. And I'm going to introduce you to another enzyme called PP1 in regards to the phosphatase, the pyrophosphatase number 1 enzyme, I think it's called, in regards to this well-fed and starving state. So again, let's put this stuff together. It's going to draw upon what we've talked about in the last 10 weeks, and we're going to start putting it together in regards to how we're going to make our cells happy, and importantly, how our cells respond when they are not happy in regards to their metabolism. So, oh my God, we've seen this one before. So obviously, we know the glycolytic pathway and the gluconeogenic pathway, and we know there's points of regulation. We know this guy here, again, that mitochondrial picture with the phosphoenol pyruvate, these are occurring with our friend oxaloacetate. And I keep bringing this friend up, this oxaloacetate, because he's going to be, again, an important component in regards to the production of glucose. And phosphoenol pyruvate, obviously, all this is consuming ATP, our generous energy source to produce glucose. But we have, again, our counterpart mechanism in regards to the phosphofructokinase number 1 and the fructose 2,6-bisphosphatase playing this key regulatory component, because the enzyme that governs this particular step 1 and 2 is our bifunctional protein. It's a Janus molecule, has 2 separate faces. One is the phosphofructokinase number 2, and the other one is the bisphosphatase number 2. So not the number 1, but the number 2. So again, a little different in regards to what's going to occur. So we're going to look at the role of this fructose 2,6-bisphosphate and the regulation and against the movement of this seesaw. So here we have the structure of the fructose 2,6-bisphosphate. So here's carbon number 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So we have the 6 carbon and the number 1 carbon here being attached to that phosphate group. So again, they have these kinetic rates. And what this particular molecule is doing is influencing those kinetic rates from if we just put a simple equation where we're looking at the fructose with a reversible arrow going to fructose 2,6-bisphosphate, we have a K1 for the production of the fructose 2,6-bisphosphate, or we have a K-1 in regards to its degradation of the fructose 2,6-phosphate, giving us this fructose 6-phosphate, which we know is intermediate. So in this case, the production of the fructose 6-phosphate is by these phosphofructokinase number 2 and the fructose bisphosphatase number 2. So again, different enzymes compared to our other ones, which are number 1s. So it gets a little confusing, but this is the enzyme that is making that fructose 2,6-bisphosphate. And again, thinking about their kinetic constituents, we're going to have different rates of action. So a bifunctional particular protein, a Janus molecule, and this particular molecule is making the 2,6-bisphosphate along with the hormonal effects, and it could be insulin and it could be glucagon, and we're going to then change what the system's going to do. So in this case, when we have fructose 2,6-bisphosphate in its concentration and a hormonal effect, we're going to see the change in the production of the fructose 6-phosphate KD in regards to its allosteric modulation to really like the phosphofructokinase number 1 to do its particular job, to actually go and inhibit gluconeogenesis and produce the fructose 1,6-bisphosphate to go through and give us that payback and make all that lovely NADH and ATP in regards to going through the process of glycolysis to produce pyruvate. So again, this is what this is saying here. The phosphofructokinase number 1, the KD, the affinity, attraction of that enzyme to the substrate, fructose 6-phosphate is increased. We're stimulating the process of glycolysis in the liver and moving the glucose down to produce pyruvate and all the other goodies associated within its degradation. In the second process, when we have the phosphofructokinase, the fructose bisphosphatase number 1 being inhibited in regards to the concentration of the fructose 2,6-bisphosphate as well as hormonal activity, we can promote, importantly, the need or movement of glucose in regards to the cell, meaning we are trying to stimulate the issue of glycogen playing a role to basically inhibit the production of pyruvate and move through the situation of gluconeogenesis. But in this case, what we're seeing is the hormonal component of insulin and the high concentration of the fructose bisphosphatase playing a role to also promote gluconeogenesis at the cost of glycolysis, promote the production of glycolysis at the cost of gluconeogenesis. So again, this seesaw of actions in regards to this statement. So again, think about number 2. We're inhibiting the fructose bisphosphatase number 1. So go back to our previous slides in regards to now inhibiting the process of gluconeogenesis to promote again pyruvate production. So again, my seesaws come in where we look at the enzyme system. So here's our first. This is the one that we are, thinking about in regards to the presence of the fructose 2,6-bisphosphate. Noting, as I said, this is where students get a little confused. This guy is being produced here with the phosphofructokinase number 2 and the fructose bisphosphatase number 2 in its degradation. So again, they look similar, but they are different. So here we have this guy playing a role. So let's have a look in A. So in A, we have a decreased concentration of the fructose 2,6-bisphosphate. With that decreased concentration, we're going to see the fructose bisphosphatase start playing its role. We're going to see an increase in glucose production, which will ultimately see an increase in blood glucose level. This is also stimulated by glycagon in regards to inhibiting the process of glycolysis and increasing the production of glucose, which is also stimulated by increased concentrations of cyclic AMP, because this is a GCPR receptor. So this is the substrate, but it's hitting a GCPR receptor to increase the adenyl cyclase to consume ATP to make cyclic AMP. So again, think about our GCPRs as we see here with the glucagon receptor and how we're using that GDP and GTP to have that adenyl cyclase to make cyclic AMP. And lo and behold, we've seen this before in regards to how phosphorylation and a regulatory site occurs within what we saw was the protein kinase A, but it's exactly the same kind of system, not structurally, but by function that we see with the phosphofructokinase number 2 and the fructose bisphosphatase number 2 in regards to how it's regulated by cyclic AMP. So again, let's keep focusing on A though. So A, what we see is a decrease in the fructose 2,6-bisphosphate. The K minus 1 is greater than the K1. So we've got a greater degradation to produce more fructose 6-phosphate. So that's this here. And then we're going to then see basically a movement to have more glucose being made. So glucagon peptide hormone has the opposite effects to insulin. So let's now change the seesaw to B in this situation where we're now seeing a high concentration of the fructose 2,6-bisphosphate being made. That means if we look back at this slide, the K1 is greater than the K minus 1 in regards to the breakdown. So we're making more of the fructose 2,6-bisphosphate. That concentration increases. It's compounded also by the concentration of insulin. And so we're seeing the greater formation. And with that insulin, we're going to see a process of moving those carbohydrates into the cell through the GLUT1 transport system, as we've all studied before. And we're going to basically shut down glycolysis because our source of energy is being met by that transportation of glucose from the extracellular circulatory system to the cytosol of the cell through the transports. So we're going to ideally see a decrease in blood concentration. But now we've got all this glucose coming into the cell, and we're going to have to do something with it. Obviously, the first thing, logically, is to metabolize that glucose and increase glycolysis to allow us to basically make ATP, make pyruvate, feed that pyruvate to another system to make more energy in the form of electron carriers, which will ultimately make ATP. So again, we have this seesaw where the insulin concentration is heavy. We're going to see the fructose 2,6-bisphosphatase increase at the expense of the glucagon, which again is going to basically utilize, when it's activated, a GCPR. So hopefully that's a little clearer in regards to this central component. But noting again, we're dealing with two isoforms of an enzyme, a phosphofructokinase number 1 and a phosphofructokinase number 2 versus the fructose bisphosphatase number 1 and the fructose bisphosphatase number 2. But they do two separate things in regards to one is a central component. The number 1 enzymes are a central component in the regulation of which we're going through glycolysis or gluconeogenesis, where the number 2 enzymes, the phosphofructokinase number 2 and the fructose bisphosphatase number 2, are producing the regulator in regards to fructose 2,6-bisphosphate. So again, keep that clear in your mind and really be able to understand that, because that will come up most probably on the exam in a combined question. So let's recap. And I know I keep going through the situation because it's so important in regards to its regulation. Here we have glucagon, we have insulin, both playing a positive role, but through the process of phosphorylation of this Janus molecule. So in this case, the process of dephosphorylation of the active one here in regards to the displacement of using molecular water is a positive in regards to insulin. This is stimulating glycolysis but inhibiting gluconeogenesis. Vice versa in regards to the decrease of the 2,6-bisphosphate, which inhibits glycolysis and stimulates gluconeogenesis due to a simple phosphorylation in regards to the utilization of the glycagon hormone, the consumption of ATP, and increasing cyclic AMP through the adenyl cyclase through the GCPR. So again, that's a recap. But this is all crazily coordinated by this phosphorylase A and phosphorylase B in regards to what we're going to do now with that surplus glucose coming into the cell. We've got insulin promoting the transportation. We're going to have to do something now with this insulin, this glucose coming in. So let's have a look what happens in the muscle when we coordinate the synthesis and breakdown of glycogen, because we don't want to be doing both simultaneously. We want to be either doing one or the other. But note, we might be doing opposite in the liver compared to what we're doing in the heart or the muscle. So again, different regulators in regards to these systems in different tissue types. So in the muscle, we have glucagon. We're going to have that be degraded to produce the glucose 1-phosphate, and that can then go off to the metabolic pathway. And that uses the glucagon phosphorylase. Now, again, think of your idling car at the traffic light. There's always going to be some level of activity occurring at a resting state or at an active state. And this resting active state is dependent on a single phosphorylation. We want a quick, rapid response in regards to going from the glycogen phosphorylase B, which is less active, to that of the active form of the glycogen phosphorylase A. And this is specifically in muscle. Okay, so here we have a little illustration in regards to the phosphorylation of the side chains of a serine moiety in the phosphorylase B. So at the resting state, we basically got our foot off the pedal, the car is turning over, we're waiting for that traffic light to actually turn, and we're going to go full speed in regards to producing the phosphorylase A active enzyme, okay? And we're going to do that due to the sensitivity of the glucagon, specifically in the liver, but also coordinating the activation of this same system in regards to breaking down glucagon as glucose 1-phosphate in the fight or flight system in regards to epinephrine in the muscle. We also see it also being sensitive to the AMP concentrations, calcium through the calmodulin. That's why we studied and looked at calmodulin. But ultimately, we're going to see the epinephrine and the glucagon playing a positive role, consuming ATP to give us that phosphorylation of the phosphorylase A to make it active, to allow us then to have this guy basically consuming glucagon to produce the glucose 1-phosphate. So again, we're switching our enzymes by a simple phosphorylation event and having them modulated in a positive way in regards to the system of the glucagon GCPR and the epinephrine GCPR, particularly with the adenyl cyclase activity to allow us to increase cyclic AMP. The opposite system has to also have, the system also has to have a regulatory control. We cannot keep the activated phosphorylase A being active all the time because we won't have any glycogen left. We're going to have to shut this down once we want to start producing glycogen. So again, we're going to have to shut down the phosphorylase A from its active form to its inactive form by removing those two phosphate positions. And we do this by using the phosphorylase phosphatase. So the phosphorylase A phosphatase, it's the phosphorylase A phosphorylase, abbreviated as PP1. This enzyme dephosphorylates the active form to give it to the resting form or less active. So we can switch backwards and forwards from this active or less active form by a process of dephosphorylation. So it's an illustration of how phosphorylation can occur. But again, it's very sensitive and very rapid response because it's a simple two phosphorylational constituents. It is best to have this system ready and primed to allow us to go and switch between the active or the less active and the active form. Now, we also see epinephrine having a role in regards to the phosphorylation of these particular serine moieties, which is great, which we also know with the adenyl cyclase, it sees this massive concentration of cyclic AMP. And again, this is where we're seeing this occurrence with these positive effects in regards to making it active. So we see the calmodulin, go back to chapter 12, in regards to playing a role and needing that calcium. And guess where that calcium is coming from? We already know the endoplasmic reticulum through the IP3 receptor, through the IP3 pathway. So the problem is we know that AMP activates various phosphatases, and this is a problem. And again, we have to have this compound very short-lived, either going back to ADP or moving its way to ATP. We also know ATP inactivates this particular system because it has to have this issue of energy balance. We do not want to produce tons and tons of glucose 1-phosphate if we don't need the energy requirements. We're being futile in regards to our breakdown of our glycogen. So we have to be sensitive in the breakdown of our glycogen in regards to the cell's needs. Because if we don't, we're going to have accumulation of glucose 6-phosphate going through the system, and it's going to be futile. So we're only going to take off the glucose 6-phosphate and go through the phosphoglucose mutase system to make the glucose 6-phosphate that can go into our glycolytic pathway only when we need it. So again, a very, very fine balance between the happy and the sad cell in regards to the ATP concentrations as well as the AMP concentrations. Now, at rest, again, this is an issue of this phosphorylation, activation and deactivation. We see this minus phosphorylation and prohibit basically the production of glucose 1-phosphate at the expense of glycogen. So at the rest, we have the inability to further degrade glycogen. And we might take advantage of this in regards to the issue of producing more glycogen to actually supplement this. And we'll have a look at that through the UDP glucose system that we talked about on Tuesday. So again, phosphorylation plays a key example of reversible activation or inactivation. So again, just a simple example of what we know in regards to allosteric modulation. Because when you add that phosphate group on, think about what you're adding to the structure. You are adding negative charges to a particular key position of the structure of the enzyme. Once you add those negative charges, you are going to cause charge repulsion. That amino acid, that serine, now has this negative charge on its side chain functionality. It might be neighboring originally a positive charged amino acid. So there actually might be an attraction to cause a steric three-dimensional structural change. It might be only minor, but it's enough to change the cleft and binding site to the substrate to cause its regulation. And vice versa, if you remove that negative charge state and produce the normal serine, it might change the structure of the molecule. It will change the structure of the molecule to then basically bring it back to a system where it's active. Okay, but again, this is just the example of phosphorylation being active and dephosphorylation being less active. But again, phosphorylation is a little bit more promiscuous in regards to whether it's activating or deactivating. So please I want to make that clear, because you might look at other enzyme systems and say, well, fat phosphorylation inhibits it, not an activator. But you might look at another system that says the system activates it and inhibits it. So again, depending on the system, it's very dependent on the enzyme that you're targeting. So this PP1, the phosphoprotein phosphatase, becomes a very important key regulator in this particular process. Now, the funny thing is, in the liver, there's a whole different load of systems, which basically are going to be sensitive in regards to the cyclic AMP concentrations. Not so much the issue of the glucagon, but the cyclic AMP, which can come from the production and degradation of ATP, ADP, AMP cyclization to make cyclic AMP. So in the liver, glycogen will still go through the same process and degrade using a substrate enzyme, the glycogen phosphorylase. And in this case, it's going to produce glucose 1-phosphate. So it can go through the phosphomutase to make glucose 6-phosphate, and that can go off into the glycolytic pathway. In this process of phosphorylation, we have a less active component, as we've seen previously, with the glycogen phosphorylase B. And in this time, we're going to activate it with the process of phosphorylation to then convert it to the glycogen phosphorylase A, which is then going to be basically increasing the degradation of glycogen and producing more glucose 1-phosphate. But this time is sensitive, importantly, to cyclic AMP. So let's have a look. Here we have an issue of hormonal and allosteric regulation. So a piece of regulation on top of a piece of regulation. And we need this to be able to, again, control the process of the phosphorylase B. So what we saw previously, we saw a system where there was no requirement for a substrate. So again, if we look back here in the muscle, there was no requirement for the substrate to bind to cause this allosteric modulation or shape change due through phosphorylation. But we're dealing with a different system in regards to now a hormonal allosteric regulation combined. So here we have glucagon playing its role, and we have these particular phosphorylase A switching to become the active form. So here's the active form here to regress back to the less active form. So it's a little bit in the opposite direction. In this case, the phosphorylase A has this empty allosteric site, which needs to be occupied by the substrate before the enzyme can be deactivated. Because what's happening with those serine moieties, when they are phosphorylated, they are buried, and they cannot be dephosphorylated until there's a structural change that occurs within the enzyme itself. The only time that enzyme structural conformation is going to occur with two moieties of glucose binding to the substrate, the enzyme, the two moieties of the glucose as a substrate binding to the enzyme to cause an allosteric modulation, a structural change, which will then allow the phosphate serines to be presented to go through the process of degradation and dephosphorylation. And with that dephosphorylation, we get the less active form. So in this case, let's have a look. So here we have phosphorylase A with it already phosphorylated, with the serines embedded in there, protecting them from enzymatic degradation. They become exposed with the binding not of one glucose, but two glucose moieties, and it has to be two glucose moieties. Once that is bound, their particular position is then exposed through a conformational change. And in this case, we have the phosphorylase A phosphatase, the PP1, coming in, doing its job, dephosphorylating the serine moieties and allowing then the phosphorylase A to have the occupied site still with glucose and be its less active form. This slows down the glycogen breakdown in response to, importantly, increased blood glucose. So it's actually consuming blood glucose to bind to the phosphorylase to cause the structural conformational change. It is also causing the degradation of the regulatory components in the phosphorylation event to allow us to produce the less active form in the glycogen phosphorylase B, and therefore promoting the holding of the glycogen and limiting or decreasing or minimizing the degradation of glycogen to produce glucose 1-phosphate. So again, this is an illustration of how hormonal and allosteric modulation work together in regards to providing us the capacity to provide a regulatory component. Insulin plays a very important role in this in regards to insulin. As I said, we are moving with insulin, increasing transportation. We are going to bring glucose into the cell because of those insulin transport systems are now being activated by the insulin binding to the insulin receptor. And therefore, we are basically trying to combat an increase in blood glucose. But now we've got this glucose coming in, we're going to have to do something with it. We've now inhibited the issue of its breakdown in regards to breaking down more glycogen and adding more glucose to the pool. So we've done that through this particular illustration. But what are we now going to do with the glucose now coming into the cell? We're going to have to do something with it, either metabolize it or put it into storage by producing glycogen. So let's have a look. So we have these two systems, and we'll have a look in a second. This is just a recap with the hepatic liver cells and myocytes, the cardiovascular cells, where they're going to have the same kind of effect in regards to epinephrine and glucagon in regards to the liver. They're all going to go through the increased moieties of producing cyclic AMP, activating various cascade events to allow us ultimately to increase blood glucose production in the liver, to get that glucose circulating into the circulatory system, to feed, importantly, maybe glycolysis in regards to providing muscle contraction if there's no glycogen stores. But the cells will actually potentially utilize their glycogen stores as much as they possibly can until it's fully depleted in regards to promoting a activation of many glycogen phosphorylase molecules to allow you to attack your glycogen polymers to give you the glucose 1-phosphate that you need. I'm going to go through the glucose mutase reaction to produce the glucose 6-phosphate, which will then basically be dephosphorylated through the utilization of the endoplasmic reticulum lumen and the transporter 2 and transporter 3 to move that glucose out from the liver to maintain and top up the glucose level in the circulatory system. In the muscle cell or in the myocardiac cell, we're going to utilize that glucose 1-phosphate to go through glycolysis to give you the energy that you need to keep that heart contracting. So again, we're going to use different systems, but ultimately there's a key central component in regards to activation of many molecules to give you the effect of breaking down your glycogen stores, whether it be in the myocardiocyte or the hepatocyte, to give you that glucose 1-phosphate. If it's in the hepatocytes, the liver cells, the priority is to make that glucose and then be a donor and shift that glucose out to the rest of the system. In the heart cell, it's going to use that glucose 1-phosphate to actually directly move that glucose 1-phosphate to glucose 6-phosphate, and then go through the glycolytic pathways to give you ATP, ultimately to provide muscle contraction. Because obviously you want to keep your heart going. So again, that was a little bit of a summary of the cyclic AMP cascade, which again illustrates the sensitivity and the differentiation between different tissues in regards to what they do at the end point in this case. The central point is the same, but the end point is different. So we've got that glucose coming into the cell due to the insulin receptor and the transporters. We've got the glycogen now synthesis being inhibited because we are working with the less active form of the phosphorylase enzyme, which is normally degrading glycogen to produce glucose 1-phosphate. So we're going to now go through another system to allow us to produce glycogen through the glycogen synthase. So with this massive amount of glucose coming in, we're going to have to do something with it. And we're going to do that by producing glycogen. And we already know how we do that a little bit already, but we're going to recap it again. So here we have UDP glucose coming in. So we have glucose. We can go through the UDP system to allow us to produce glycogen by using a glycogen synthase. With a glycogen synthase A, which is a highly active enzyme in its phosphorylated form. And in its deactivated minus the phosphorylational form, its, dephosphorylated form is active. Minus phosphate. Hang on, so I've got to check this one. Give me a second, let me think. Dephosphorylation. I think that is wrong. It's the phosphorylated form that is active. Minus phosphate. Yeah, I've got it. I have to check this one because I think I've got this. This is supposed to be phosphorylated form is active. Let me check that. I'll put a correction on the slides because I think that's wrong. So what we see is this active form in regards to its I have to check that. I might have that piece wrong. But anyway, what we're seeing basically is a phosphorylation change in regards to activation and deactivation through this guy here, the glycogen synthase. The glycogen synthase is that key component where we're going to be utilizing the glucose UDP system to allow that leaving group, the UDP group, to promote the binding of the glucose moiety in the 1,4 configuration on the non-reducing end of the elongating chain of glycogen. We've already seen that. So in this case, what we're going to see is ultimately the regulation of this guy, because we want to promote this in regards to, if we have the substrate to do it, we're going to promote this guy to allow the substrate to elongate the chain of glycogen. If we have an inhibition of this, again, we're going to have a seesaw mechanism. We're going to inhibit the production of glycogen and then promote the degradation of glycogen, as we've seen in the previous slide. Let me check this slide and I'll make a comment and I'll send an email out because I think it's supposed to be dephosphorylation. So we've seen this picture before. Here we have the insulin substrate number 1, the protein kinase B, importantly the inactivation by phosphorylation of the kinase substrate number 3 and its role importantly in the regulation of the glycogen synthase. In this case, having this guy present is going to, in its active form, is going to shut down the glycogen production in regards to its phosphorylation. The absence of this particular compound, we move it through by phosphorylating it, causing a three-dimensional structural change by the protein kinase B, and we're going to see this guy moving away and allowing then the glycogen synthase to be active in regards to its dephosphorylated form. So we've already seen this particular system, but we're going to have a little more closer look here in regards to the glycogen synthase, because it's going to have some aspects that we've previously seen in regards to autoregulation, as well as the role of the PP1 enzyme here. So let's have a look. Glycogen synthase B, which is the inactive form, and glycogen synthase A, which is the active form in regards to phosphorylation. So in this case, we're going to see a simple transformation of this particular process in this dephosphorylational component using the phosphophosphatase number 1 enzyme and causing its deactivation and giving us off those 3 phosphate groups. Once that phosphate groups are off the glycogen synthase, it is now active. Okay. Now, we also see its deactivation occur in sensitivity in regards to consuming ATP moieties through the glycogen synthase kinase number 3 and bringing it back to its inactive form. This is extremely sensitive. The glycogen synthase kinase number 3, as we've now seen, is apparent in regards to its inhibition through insulin. So the vice versa has to also be correct when we want to see the movement of the inactivated form going to the active form by utilizing, again, insulin, which is having a positive effect, glucose 6-phosphate, because that's going to be a substrate, having a positive effect, as well as its final intermediate or final constituent in glucose also having a positive effect in regards to moving the glycogen synthase through to becoming active to allow us to produce glycogen, because it has the substrate. So these substrates are needed. It's no good activating the enzyme if you don't have the substrates available. This is why these guys are particularly active in activating the enzyme in regards to the PP1. Insulin also has a positive effect. Now, glucagon and epinephrine have a negative effect, because what we want to see is basically no more glycogen synthase being synthesized in the flight or fight mechanism. We want to be able to say, stop glycogen synthesis, now work on glycogen degradation, because we need those glucose moieties. So again, glucagon and epinephrine have a negative effect on this enzyme in prohibiting and ensuring that the system is going to be in its active form, in its inactive form. So glycogen synthase A is the active form, glycogen synthase B is the inactive form. Insulin blocks the activity of the glycogen synthase and activates the PP1 enzyme. And we already see that that glucose binding also promotes the dephosphorylation. So that goes back to, where are we? This slide here. Okay, the addition of allosteric and hormonal regulation. Now, with the glycogen synthase kinase number 3, we need those 3 phosphorylation events to occur to give it its inactivation. So again, 3 additions of 3 negative charges on a serine moieties cause a 3-dimensional structural change, which will inhibit the glycogen synthase B from binding its substrate, in this case, UDP glucose, okay? So in this case, we're killing the enzyme system and not allowing it to do its job. If we remove one phosphate, it still is deregulated. Second phosphate is still regulated. The third phosphate has to be dephosphorylated to bring it to the active form. Now, in the liver, we need to have the PP1 doing the removal. So that's the guy who's going to be regulating the movement from the inactive and the active form. And we also know, again, glucose 6-phosphate is going to be a modulator because it provides a better capacity to then give you glucose consumption as a substrate to allow you to make UDP glucose and then go through the whole process of activating the glycogen synthase to make more glycogen. Okay, so again, this is all illustrated on page 611. Have a read of that, and I will check that particular slide. I'm going to have to make sure that I am right. Okay, we've got a few minutes left. Now, the glycogen synthase number 3 enzyme also has a process of autoregulation. And we've talked about autoregulation already in regards to the issue of enzyme site binding to itself to cause an occlusion. This also happens with the glycogen synthase kinase number 3. So here we have our glycogen synthase and our glycogen synthase enzyme doing its job. It's going to consume ATP and phosphorylate, importantly, a particular serine position. And it needs to add 3 serine phosphorylational groups to produce the inactive form. Okay, so remember the inactive form is dephosphorylated. So in this case, we're going to see the addition of 3 phosphates to the glycogen synthase to inactivate it. But this cannot occur unless there is a priming system. And we've seen this priming system here. So to transition the active form to the inactive component, we need to rely on another enzyme, a kinase. I think it's what's it called? A casein kinase number 2. The casein kinase number 2 to prime the whole phosphorylation event. Remember, I told you take 1 off, take 2 off, take 3 off. Until you've got all that 3 off, it's still in its inactive state to be active. But with this particular system, we basically use this casein kinase number 2 to prime the whole situation, to allow the ATP molecule to give its phosphate group off, to prime the glycogen kinase number 3 to bind to the glycogen synthase. Without that particular priming, we are not going to get the glycogen synthase to work. So this is a separate event to this. So again, phosphorylation occurs on the glycogen synthase kinase to prime then the interaction with the glycogen synthase to then continue with 3 additional phosphorylation events. So in this case, we have to have a priming system to occur. So with that priming component, we have 1, 2, 3 sites ready to actually be phosphorylated with the glycogen synthase. But the glycogen kinase synthase number 3 also has this capacity to autophosphorylate or use what we call a pseudo substrate. And this leads to its autoregulation. See, here we have the phosphate group on the glycogen synthase, which is primed by the casein kinase number 2. But we also have this capacity with this particular arm of the glycogen synthase to mimic this particular priming component. But in this case, by mimicking the priming component within itself, as the glycogen synthase does here, as shown here, we inhibit the glycogen synthase kinase number 3 from doing any work. So in this case, we are basically going through a process of auto-inhibition. So again, the casein kinase number 2 is a priming event to allow us to have this to occur, to allow the glycogen synthase kinase number 3 to initially bind to the glycogen synthase substrate. And again, we can have auto-regulation and manipulation to basically go through pseudo-substrate interactions to cause a regulational component. Now, this is actually easier to take off because it is an auto self-inhibition and the protein is containing this serine in a very localized position. So if we dephosphorylate this, obviously it opens it back up and allows it then to bind to the glycogen synthase substrate only if the glycogen synthase substrate has that priming phosphate position on it. So again, we now have 3 steps of regulation occurring in this particular enzymatic system. We have autophosphorylation, we have priming phosphorylation, and we have also the issue requirement of the substrate, as we have seen here with glucose and glucose 6-phosphate, as well as insulin. But insulin is more getting that glucose into the cell and that glucose 6-phosphate being primed from glucose to glucose 6-phosphate. So again, multiple regulators. It gets further complexing as we get through. So we also have the role of insulin with the glycogen synthase kinase pathway and its regulation of glycogen synthase also. We need to be able to, again, coordinate these very carefully because we want to be able to have the insulin receptor matching the movement, though it's not shown here, the movement of the glucose into the cell, going through the various substrate receptor coordination with the protein association with PIP3 and PIP2 and the increased cyclic AMP and everything else. But in this case, the whole system here is to phosphorylate the insulin receptor substrate number 1 to interact to allow the activation of the protein kinase B. With that protein kinase B, we're going to see phosphorylation of the substrate here, which is glycogen synthase kinase number 3, which is normally activated to basically cause its inactivation. So we're here seeing an activation of a phosphorylation group to cause its inactivation through phosphorylation. So again, multiple steps, different types of phosphorylation, dephosphorylation, phosphorylation causing its regulation. In this case, we have the active glycogen kinase number 3 being phosphorylated by the protein kinase B to then cause basically its removal to allow the PP1 to actually do its work to activate the glycogen synthase kinase number 3 through dephosphorylation. So here we have an event, importantly, of a dephosphorylated enzyme causing the phosphorylation of an enzyme to be deactivated. With the removal of that protein kinase substrate, the glycogen kinase number 3 by the protein kinase number B by its phosphorylation, we then see also the inactivation, okay, through phosphorylation. So in this case, we will see this in response to the decreased blood glucose and also then increasing glycogen synthesis because the blood is depleting the glycogen stores. The blood is decreasing its glucose concentrations at the expense of the transport system, promoting, importantly, an active form of glycogen synthase to take that incoming glucose to then elongate our glycogen chains to increase our glycogen stores. So we're depleting the blood glucose, we're increasing the glycogen synthase by utilizing the insulin receptor and this glycogen synthase kinase number 3 in its phosphorylational dephosphorylation event and its effect on the glycogen synthase kinase, the glycogen synthase. But again, we have that auto self-priming regulational component with the casein kinase number 2, which is essential for this phosphorylation event to occur to cause its deregulation. I think we're going to leave it at that and we'll do a little bit more. I'll go back through this part again and I'll check that component in regards to that statement. I am pretty sure this is supposed to be dephosphorylated, but I could be wrong. Let me check my notes and the book.